Wavefront sensing helps us to understand the complexities of refractive surgery. We are now able to evaluate and measure the entire optical system of the eye. The wavefront map demonstrates the outgoing wavefront over the pupil with the ideal wavefront printed green. The map represents the wavefront at the time point of one measurement, but short-acting factors like tear film, vitreous floaters or accommodation influence the highly sensitive measurement to a marked extent. Only by using a dynamic measurement can these factors be identified. Our purpose was to dynamically and objectively measure accommodation in eyes with crystalline lenses or different IOL designs using a wavefront aberrometer to simultaneously monitor low and high order aberration changes. Therefore, the Asclepion Wasker Wavefront Analyzer workstation was modified. In wavefront analysis, usually the eye is illuminated by a plain infrared wave emitted by a superluminescence diode. The light is focused on the retina by the refractive power of the cornea and the lens. The resulting focus acts like a point light source on the retina. The light goes back through the optical apparatus of the eye. The shape of this wavefront exiting the eye describes the optical system of the eye. The spatial phase distribution in this wavefront is investigated using a Hartmann-Shack sensor, which consists of an array of microlenslets and a CCD chip detector placed in the focal plane of the lens array. Each lens defines a subaperture focusing a small portion of the incident wavefront on the CCD sensor, leading to a pattern of focal spots on the detector surface. This pattern contains the information about the spatial phase and intensity distribution of the incident wave. Patient alignment, including focusing and centration, is accomplished with the assistance of a continuous live video image. The aberrometer allows us to capture a sequence of consecutive measurements at a frequency of 7 Hz in order to provide information on dynamic changes of both refraction and aberrations. The complete dynamic wavefront measurement took approximately 30 seconds. During this period, about 200 single wavefront measurements were taken and analyzed. The patients initially focused on a distance target at 4 meters for 10 seconds, followed by focusing on the near target at 22 centimeters for 10 seconds. Then the distance target was focused on again for an additional 10 seconds. Results are presented as a graph as well as a 3-dimensional wavefront chart. This example of a young phakic eye shows the refractive data in the state of distance accommodation. The blue line represents the spherical equivalent, the pink line the sphere, and the yellow line the amount of cylinder. This equals his subjective refraction of 0.5 combined with 1.5 at 5 degrees. The patient now changes to the near target at 22 centimeters. This results in a change of sphere and a slight change of the amount of cylinder. After focusing back to distance, the refraction returns to the initial values. Regarding higher order aberrations, major changes during accommodation are seen in the spherical aberration, which is represented by Zernica 40. This effect can be explained by change of curvature of the crystalline lens surface during accommodation. The 3-dimensional animation of the dynamic wavefront map shows the whole wavefront. Here, the dynamic wavefront of high-order aberrations can be seen. As the focus point shifts to near, significant changes in both maps can be seen. This example of a pseudophakic eye with an array multifocal IOL with good visual acuity shows a slight change in spherical equivalent, but no changes in higher order aberrations. Especially Zernica 40, which has shown significant accommodative alterations in the phakic patient, remains unchanged. A certain proportion of patients implanted with standard IOLs appear to have functional near vision. Forward movement of an IOL induced by accommodative effort of the ciliary muscle has been reported by several authors, including Fukasaku, Lesivska, and Thornton. The AT45 crystal lens from C&C Vision is essentially a plate haptic silicone IOL with polyamide haptics designed to allow antero-posterior movement of the lens along the axis of the eye, thereby providing near, intermediate, and distance vision. The plate length is longer than the bag, and the IOL is hinged at the junction of the plate haptics with the optics. This configuration results in the 4.5 mm optic being somewhat retroplaced once the IOL is inserted into the capsular bag. The theoretical mechanism of efficacy of this IOL is based on the concept that with accommodative effort, redistribution of the ciliary body mass will result in bulking posteriorly and impinging or pressing on the vitreous face peripherally, increasing vitreous pressure. This forces the optic forward anteriorly within the visual axis, creating a more plus-powered IOL. A similar mechanism is assumed in the one-piece acrylic 1CU accommodative IOL from Human Optics. The relaxation of zonular fibers leads to a relaxation of the capsular bag. This relaxation leads to an anterior motion of the optic via a hinge at the optic-haptic junction of the four haptics. The haptics rotate anteriorly and thereby relax the hinge area, thus resulting in an anterior movement of the optic, as can be seen in the computer simulation based on finite elements calculation. This dynamic wavefront is an example of a pseudophakic patient with a 1CU lens. Although being pseudophakic, the refraction shows an amplitude during accommodation in sphere of about 0.75 diopters and a slight change in astigmatism. The spherical aberration, and therefore Zernica 40, does not change, since the curvature of the lens is not affected by the antero-posterior movement of the IOL. Previous methods of measuring the eye's wave aberration can measure only the static properties of the wave aberration. The Wasker wavefront analyzer effectively monitors the dynamic accommodation process. This highly reproducible measurement provides an objective characterization of changes of the pseudophakic's eye's aberrations beyond defocus. It allows us to investigate the functionality of accommodative IOLs irrespective of their underlying functional thesis. The optical quality of the phakic eye is best at the resting point of accommodation. Aberrations increase for targets both nearer and farer from the eye. Accommodation produces significant changes in coma, although the direction of the change varies with individuals. These changes are consistent with changes in the relative centering of the lens and cornea, which probably occur as the lens moves during accommodation. For the first time, changes in refraction as well as in aberration were objectively and automatically measured in pseudophakic eyes. Information on the change in the overall wavefront aberration as well as the individual aberration was obtained. Some of the aberrations arise from a slight distortion of the IOL due to the process of accommodation. Systematic changes in spherical aberration and variable changes in coma with increasing accommodation are consistent with the motion of the IOL during accommodation. In 24 of 27 eyes with different accommodative IOLs, an accommodative amplitude of different heights ranging from 0.5 to 2.75 diopters was detected. Obviously, additional factors like changes in aberrations contribute to the functionality of these various accommodative IOL designs. This dynamic wavefront evaluation method allows us to advance our knowledge in the field of accommodating IOLs towards the ultimate outcome, complete patient satisfaction.